Placement groups allow you to enhance the network performance of your instances. They help reduce latency, which is the delay in communication, and increase throughput, which is the amount of data transmitted over a network in a given time. By using placement groups, you can better control how your instances interact, ensuring they work together smoothly and reliably. Think of it like a team of runners in a relay race. If they are positioned close together and have a clear path, they can pass the baton quickly and maintain speed. Similarly, placement groups help your instances stay connected and perform at their best. In summary, placement groups are essential for optimizing network performance and improving fault tolerance in high-performance computing workloads. Cluster placement groups are designed to arrange instances in a single rack. This tight packing is crucial because it significantly reduces latency and increases network throughput. In simpler terms, when these instances are close together, they can communicate more quickly and efficiently. This setup is particularly beneficial for high-performance computing tasks, where speed and efficiency are paramount. Think of it like a group of friends sitting closely together at a table. When they're all nearby, they can share ideas and have conversations much faster than if they were spread out across a large room. Similarly, by clustering instances, we ensure that data can be processed and shared swiftly, which is essential for tasks that require rapid computations. In summary, cluster placement groups optimize the arrangement of computing instances to achieve lower latency and higher throughput, making them ideal for demanding computing applications. A spread placement group distributes instances across different hardware. This means that if one piece of hardware fails, the other instances remain safe and operational. This setup is particularly useful for critical applications that rely on a small number of instances, ensuring that they are protected from hardware failures. On the other hand, we have the partition placement group. This is designed for large-scale distributed workloads. In this setup, multiple partitions are created, and each partition operates on independent hardware. This way, if one partition encounters a failure, the impact is limited, and the other partitions can continue functioning smoothly. To recap, spread placement groups are ideal for critical instances needing high availability, while partition placement groups are suited for larger workloads that can be divided into independent parts. Understanding these differences helps in making informed decisions about resource management in cloud environments. First, let's visualize the cluster architecture. It's like a high-speed local area network, where all the components are closely connected. This setup is designed to minimize latency, which means data travels quickly between instances. Next, we have the spread architecture. This one is set up across geographically separate racks, providing fault tolerance. If one rack fails, the others can still function, ensuring that our system remains operational. Finally, the partition architecture divides multiple racks while maintaining isolation. This design enhances distributed resilience, allowing the system to recover from failures more effectively. To put this into perspective, think of cluster as a fast train running on a single track, spread as a network of trains that can reroute if one track is blocked, and partition as separate train lines that operate independently. In summary, each architecture has its strengths: cluster for speed, spread for reliability, and partition for resilience. When validating, it's important to avoid common mistakes. One mistake is selecting the wrong placement type for your workload. For instance, if you have a workload that requires low latency, but you choose a placement group that doesn't support that, you could face performance issues. Another mistake is launching a large number of instances in a spread placement group, which can lead to inefficient resource usage. Additionally, missing the configuration for partition groups can result in unexpected failures. To take a safe approach, first identify the type of workload you have. Based on that, choose the appropriate placement group. For example, if your workload is sensitive to latency, you might opt for a cluster placement group to ensure optimal performance. In summary, validating your workloads requires careful consideration of placement types and configurations to avoid common pitfalls. First, we talked about clustering for high performance. This means grouping resources together to work efficiently, ensuring that tasks are completed quickly. Next, we have spreading, which is all about fault tolerance. By distributing resources across different locations, we can protect our system from failures. If one part goes down, the others can still function, keeping everything running smoothly. Finally, we discussed partitioning for distributed resilience. This involves dividing data or workloads into smaller parts, allowing the system to recover quickly from issues and maintain availability. Think of it like a team project. If everyone works closely together, they can achieve high performance. If one member faces a problem, the rest can continue working, ensuring the project stays on track. In summary, clustering enhances performance, spreading ensures fault tolerance, and partitioning provides resilience. If you found this video helpful, please like, subscribe, and let me know in the comments which was architecture topic you'd like to explore next.